Okay, welcome to another operations research video. Today is the first day where we start thinking about how to solve linear programs using the simplex method. It's going to be a series of videos kind of diving into the simplex method. And here we've got Geppetto's problem again. We introduced Geppetto's problem in a previous video, but it will be featuring prominently over the next couple videos as we discuss and think about the simplex method. So here's the description of it. Feel free to pause and read it. I'll also have a scanned version of this linked on Moodle as well. Here's essentially the formulation for the linear program. We got two decision variables, the number of soldiers and the number of trains, which we'll use as x with a subscript of s and x with a subscript of t. Change those up a little bit from the previous videos. And then we've got our objective here and three constraints dealing with the finishing, carpentry, and demand for the products, and then also the non-negativity constraints. I've gone ahead and sketched the feasible region here. This region right here is the feasible region that's below and to the left of each of those constraint lines while still being in the first quadrant. I haven't shaded it in because we're going to be adding to this sketch in a little bit. So I encourage you maybe pause the video and copy down a version of this sketch so that you too can add to it as well. So feel free to kind of also sketch it up in Desmos if you want, but it'd be nice to have a paper and pencil one so you can annotate it as well. So first topic we want to introduce on our way to the simplex method is a little bit about the way that we write our linear programs. So we'll introduce this idea of standard form and then augmented form. So a linear program can have equality constraints, greater than or equal to constraints, or less than or equal to constraints. But oftentimes, eventually, we're going to want to put it into augmented form where they all become equality constraints. Note that we never have strict inequalities in our constraints. And maybe I'll leave that to you to think about why we can't do that. Especially since, as I introduced last time, all our solutions are going to be on the boundary. And what would it mean if our boundary wasn't included in the sort of allowable, feasible space? Okay. So two formats for either maximization or minimization form that we'll call standard form. For a standard form, for maximization, all the constraints are less than or equal to. So we're trying to make something as big as possible, but we're limited by some less than or equal to constraints. You can think of this as maximizing profit under limited resources. So Geppetto's problem is a great example of that. We want to maximize profit, but we've got a limited amount of some various resources, and those limited resources make up our constraints. For a minimization problem, on the other hand, the standard format will have all greater than or equal to constraints. You can think of the prototype for this one being minimizing cost, but you've got some required activities that make up your constraints. And so you might think of Bajarni's steak and potato diet problem. He wanted to minimize the cost for his diet that was strictly steak and potatoes, but he had some greater than or equal to constraints that he needed to meet his minimum requirements for, I think it was protein and carbs. And so, yeah, there was some minimum requirements while still minimizing cost. Okay, and so that's maybe another example of standard form there. So these are usually the formats that we use when we're formulating the problem, when we're writing it up, when we're entering it into the computer. Often standard form is what we want it to be in. But when we go to solve it, or at least under the hood, when the computer goes to solve it, it will take whatever we give it in standard form, or even if we don't give it to it in perfect standard form, and modify it into an augmented format. And this augmented format is the format that we'll put our problems into in order to use the simplex method. In augmented format, we'll change all the constraints to be equality constraints. So how do we do that? How do we change inequality constraints into equality constraints? And the way we do that is by introducing new variables, slack and surplus variables. And these slack and surplus variables kind of play a role. For a less than or equal to constraint, we add a non-negative slack variable to the left-hand side to change it into an equality constraint. And so I often think of if we've got a less than or equal to constraint, we do a plus, a slack, and then that becomes an equality. This variable essentially takes up the slack in our constraint because with a less than or equal to constraint, we're either, if we're strictly less than it, then we have some slack, some extra room, and this variable s is essentially going to take up all that extra room in order to make the inequality into an equality. If we have a greater than constraint, then we're usually above or at the boundary. If we're above that boundary, we've got some surplus. And so we're going to subtract off a non-negative amount of surplus. And so a greater than constraint goes to, we're going to subtract a surplus variable and change it into an equality. And then if we have an equality constraint, we don't need to do anything to change it to put it into augmented format. Later on, we'll deal with having to maybe add some extra variables even to our equality constraints to get started with the simplex method, but we won't worry about that now. Okay, so let's actually add those variables and change the constraints for Geppetto's problem. So in Geppetto's problem, we've got all less than or equal to constraints. And so for each constraint, we'll add a new slack variable to take up the extra slack. And so this constraint here for finishing, we're going to have 2xs plus xt, and then we're going to introduce a slack variable to pick up any extra that might make this actually be less than 100. And so I'm going to call my slack variables, I usually have an s as the variable, and then I'll give a subscript that relates to the constraint, because you want to think of these slack variables and surplus variables as being related to the constraint. And so I'm going to call this SF for the slack for the finishing constraint. And then that becomes equal to 100. Okay, if it helps you think about it, this SF, what is that? Well, if we kind of move everything over the other side, SF is 100 minus 2xs minus xt. It is every bit of extra that this constraint was, that the left-hand side was less than 100. So that is essentially what goes in there. And as long as SF is bigger than or equal to 0, this constraint is satisfied. Okay. So let's go ahead and do that with the rest, and then we'll kind of illustrate pictorially down below what we're meaning about for each of these. Okay, so this one, let's see. So we're going to take this constraint. It's a less than or equal to constraint. And so we're going to copy down the left side. And then we're going to introduce a slack variable, and it's going to be a different slack variable than the first constraint. So I'm going to introduce a new slack variable. I'll do plus SC, C being carpentry. So this is the slack variable for the carpentry constraint. And then that inequality becomes an equality with the right-hand side of 80. Last constraint becomes XS plus S, I'll use D for demand, equals 40. And now I've got not two variables, but now I've got 5 variables. And so my variables are now XS, XT, SF, SC, and SD, and all of those should be greater than or equal to 0. Okay, so that's how you transform them for slack variables, or for less than or equal to constraints, you add slack. For greater than or equal to constraints, you subtract the surplus. Beautiful thing is that both slack and surplus start with S, and so I'll use S to denote either slack or surplus variables. The difference will only be whether we add or subtract them to the constraints to make them into equalities. So here's the important part about slack and surplus variables, is that they encode which side of the constraint we're on. If the slack variable or the surplus variable is positive, bigger than 0, then we're on the correct side of the constraint and away from the constraint. So we're not on the boundary of the constraint. That constraint isn't going to be a limiting factor. If S is less than 0, then we're actually on the wrong side of the constraint, and the original constraint is violated. And then the third option is if we're equal to 0, then we are exactly on the boundary of the constraint. The original constraint is satisfied, and that constraint is limiting, meaning that we can't do any more of some of our variables without going outside of that constraint. And so that constraint is actually limiting us. Okay, so let's actually look at Geppetto's problem, and let's think about where those variables are, or kind of the different sides of that. And so let's choose one of the constraints. I'm going to choose the finishing constraint first, which this line represents the boundary of the finishing constraint. And so along that line, I'm going to kind of turn the paper just a little bit so I can write sideways along that line. Along that line, that is where SF equals 0. Okay. On this side of the line, the correct side of the line, we've got SF is positive, bigger than 0. And then over here on this side of the line, we have SF is less than 0, negative. Okay, and so if we're on the correct side of the constraint, that slack variable is positive. If we're on the constraint boundary, that slack variable is 0. And if we're on the wrong side of the constraint, that slack variable is negative. Okay, and we could do the same thing for each of the other constraints as well, the demand constraint and the carpentry constraint. Along this line, SC is 0. If we're below that line, SC is positive. If we're above that line, SC is negative. Similar with demand, if we're on it, SD is 0. If we're to the left of it, SD is positive, and if we're to the right of it, SD is negative. Okay. Let's actually choose a point in space, and I'm going to choose a point that's maybe not on any of the constraints. So actually, I'm going to choose this point right here, and that's the point 2020. And so let's look at the point 2020, where XS equals 20 and XT equals 20. And let's figure out what are the values of our slack variables at that point. So at that point, if I plug in 20 and 20 into each of these equations, I'll notice once I fill those in, I've only got one of the slack variables in each of those equations, and so I can solve for each of them. And so then if I look at finishing, I'll have 2 times, okay, resuming, actually got a phone call in the middle of recording. Okay, so if we plug in 20, we've got 2 times XS, which is 20, plus XT is 20, plus SF equals 100. And so this is going to be 40 plus 20 is 60. And if I subtract that over the other side, that will tell me that the first constraint has 40 units of slack, which means that if we were to choose to make 20 soldiers and 20 trains, then we'd have 40 extra hours of finishing labor. Okay, and so you can think of these slack variables as having whatever units the constraint had. And so that first constraint was talking about hours of finishing labor, and so we've got 40 extra hours of finishing labor. If we look at carpentry, let's see, we got XS plus XT plus SC, so 20 plus 20 plus SC equals 80. 20 plus 20 is 40. I'm going to subtract those over the other side, and I guess SC is also equal to 40. And so if we make 20 soldiers and 20 trains, we've got 20 spare units of carpentry labor. And then if I look at demand, that's XS is 20 plus SD is has to be equal to 40. And so if I subtract 20 from both sides, that will give SD equals 20. And so what you'll notice about each of these is because I chose a point on the interior of the feasible region, there's a positive amount of slack in each of those constraints. Okay. Let's choose another point, but this time we'll choose a point that's on the boundary. And so let's choose this point up here, the 20 and let's see, yeah, let's choose this point up here, 2060. And let's do that same computation. Compute how much slack there is. I encourage you to actually pause the video at this point, do these same computations using 20 and 60 for XS and XT instead, and pause the video, try it, and then unpause the video, and we'll do it together. So finishing, we'll have 2 times 20 plus 60 plus SF equals 100. And if we add up these numbers on the left-hand side, that's 100 plus SF equals 100. So that tells us that SF equals 0. For carpentry, we get 20 plus 60 plus SC equals 80. 20 plus 60 is 80. Subtract 80 from both sides, and we get that C equals 0. And then our demand, we'll have 20 plus SD equals 40. And so SD equals 20. So interpreting this, at the point 2060, where we're making 20 soldiers and 60 trains, we've got no slack in our finishing hours. We are using all of the finishing hours that we have available. We have no slack in our carpentry hours. We're using all the carpentry labor that we have. We have 20 units of slack in our demand for soldiers. Means that there's 20 units of unmet demand for soldiers, which in this case is perfectly fine, but we have some slack in that constraint. Constraints with positive amounts of slack actually don't affect the optimal solution. That's this constraint over here, and we can notice that the point 2060 is not on that constraint, and so we're going to have a positive amount of slack for that, the slack variable that corresponds to that constraint. Okay, let's do one last example. Let's choose this point over here, 4040. Now you'll notice 4040 is actually outside of our feasible region now. And so if we look at finishing, again, I encourage you to pause and try it yourself. we'll have 2 times 40 plus 40 plus SF equals 100. And that will give us 2 times 40 is 80, plus 40 is 120. If we subtract 120 from both sides, that gives us that SF equals negative 20. Okay, and then carpentry, we'll have 40 plus 40 plus SC equals 80. 40 plus 40 is 80. Subtract 80 from both sides of that equation, and we'll get SC equals 0. And then demand, we'll have 40 plus SD equals 40, subtracting 40 from both sides, and we'll get that SD equals 0. Okay, so the point 4040 is on the constraints for demand and carpentry. It's on the boundaries of those two constraints, but it's on the wrong side of the finishing constraint. And so this is outside the feasible region because we've got one of our slack variables with a negative value. Okay, and that's really the powerful thing about these slack variables. Two things is, one, they change our inequalities into equalities. When we're doing the linear algebra is much nicer with equalities rather than inequalities. So first off, we can kind of manipulate these with matrices, which is what we'll do a little later on down the line. And then of course, computers love thinking in terms of matrices. Okay, so equalities much nicer than inequalities. The other thing is that these slack variables encode which side of the constraint we're on. If the slack variable corresponding to a variable is positive, we're on the right side of the constraint and away from the constraint. If the slack variable is 0, we're on the boundary of that constraint. That resource, whatever it is actually limiting our production. If we have a slack variable that's negative, then we're on the wrong side of the constraint. So that essentially sums up this idea of augmented form and introducing slack variables. It's a pretty powerful idea when we get into the simplex method. So that's it for this video. Catch you in the next one.